Everybody is ready? So we are going to have problem session now. Before the problem session, let me just make a couple of small announcements. The bus to hotel will be leaving at 9:30 from the same location. Oh, 1:30. So after problem session, you can take a bus and go to hotel, and then various people have different plans about what to do in the afternoon. So everybody can decide for him or herself. One other small reminder: if you want to go for dinner tomorrow but have not registered yet, I would recommend to do it today. Well, in the worst case, tomorrow, but don't forget to register. You cannot just come without being on the list. And yeah, I think that's it.
Okay. All right, so I have the dubious honor of running the problem session. So I guess the way I've seen this work before is that we sort of try to get volunteers to go to the board and explain certain problems related to the conference. I mean, you can talk about your other problems too if you want, but but maybe don't write them on the board. So are there any volunteers to start us off? Where's Harold? Chaim, you want to start us? Okay. And how shall we do the microphones? Do you want to give him the? You want to just use this microphone?
Yeah, that's fine.
Okay.
Yeah, or I can talk loudly.
Okay.
Okay, I hope Harold's going to volunteer because he's been telling me some wonderful problems this week. So I think we definitely want to hear those. Is Harold here or has he disappeared? Okay, any rate, well, I think, you know, one problem that we should definitely have in mind with sort of minimax is the Smale conjecture. So I've sort of mentioned this before in print, but I thought I'd just mention it, you know, to the audience because it's sort of such a beautiful question. There's, of course, the solution of Hatcher, but that's a very, very complicated argument. And so Yao had suggested a very simple minimax model for how one, or a flow model for how one might tackle the Smale conjecture. So this is to put a nice metric on S2 cross R. So people haven't seen this before. It's just seems so obvious it should work. The question is really subtle issues about multiple solutions, multiple coverings and index. So you take S2 multiplied by R, and you take a nice metric which is SO3 invariant, where there's a unique stable minimal two-sphere in the middle. So we know what the minimal two spheres look like. There's just one. And so the question, the Smale conjecture, which is that diff S3 is homotopy equivalent to O4, is equivalent, and it's not too difficult to prove, to show that the space S of embeddings of the two-sphere in this isotopic class, so we're looking at all the two spheres isotopic to this guy in the middle, that this is contractible. And so if it's not contractible, obviously, then there's and of course, this is an infinite dimensional space, but it's not extremely unpleasant. It's homotopy equivalent to a CW complex, so it's not too bad. So in particular, if it's not contractible, that implies pi I of S equals HI of S is non-zero for a first I. Now the first dimension where there's a non-trivial cycle, so if there's a non-trivial cycle, you can try and do a minimax, and so you look at the, what's the minimax 2 sphere, and the minimax 2 sphere can only be a multiple of S2 because there isn't anything else. So this cycle must give you n times S. This guy here, S zeros. And that doesn't seem right, that that should be true. And of course, n algebraically, geometrically, n is going to be some odd number, but algebraically you just get it, it's just covered once. So the question is, get a contradiction out of this argument. So this would give an extremely elegant solution to Small conjecture. There still are some unsolved topics in the Small conjecture. For example, no one has written down an argument for diff RP3. So the homotopy type of that has not been written down. It's sort of clear what it should be, but it's not known. And so if you could solve this, then it's easy to see you could also solve that by a similar method. So I think there's a very beautiful question. Minimax would seem like an obvious way of trying to tackle it, but it seems very challenging. So maybe tomorrow we might hear, I know that some issues that might help with this. Okay, so that's sort of very challenging problem, but very interesting one to think about. So maybe I can pass over to Harold to give one of his nice problems.
Harold, do you have any problems you'd like to share with us? You can just use that one if you want.
So this is concerns area of minimal surfaces. So let me just define some numbers. Suppose I take a compact closed 3 manifold, or Riemannian 3 manifold, and I look at the space of embedded compact closed minimal surfaces, M of M. So this is all closed embedded minimal surfaces. And let's suppose everything is orientable. I have lots of problems with understanding non-orientable minimal surfaces, even embedded ones. So everything is orientable. So what I'd like to do is look at some numbers, M1 of M, which is the infimum of the area of all such closed embedded minimal surfaces. Okay, so just by monotonicity, we know that this number is positive. Then you can ask yourself the question, well, what about the next stage? That is, so I can look at this function f from all such minimal surfaces to R, just the area function. And I can look at all those minimal surfaces of area M1 of M. So these are all closed embedded minimal surfaces whose area is less than or equal to the area of any other closed embedded minimal surface in M. Now, Fernando has proved that this is non-empty, which is non-trivial. There is a closed embedded minimal surface that has less area, less than or equal to area than any other closed embedded minimal surface in M3. So you can consider M2 of M equal to the infimum of the area of all closed embedded minimal surfaces that are not in S1. So you're looking at the next stage. So M2 of M is greater than or equal to M1 is greater than 0. And you look at S2, etc. So you have these area numbers associated to any Riemannian closed three-manifold. And the question is, what can one say about these numbers? What relationship do they have to the geometry of M? What's the behavior? So what's the simplest three-manifold that's compact where you can hope to calculate things? The round three-sphere. And we know, in this case, what M1 of the three-sphere is. We know it's equal to 4 pi. But if you think about it, how do you prove this? Well, I can think of two proofs, and neither one of them is obvious. And both of those proofs that I know of are not invariant on the small perturbations of the metric. So you could say to yourself, well, what happens when you perturb the metric for these numbers mi? For example, a Berger sphere that's close to a round three-sphere. It's not obvious what's happening. In any case, M1 is 4 pi, and then a very deep, beautiful theorem of Fernando and Andre says that M2 is equal to 2 pi squared, the area of the Clifford torus. Now, what happens after M2? So in their paper on the Wilmot conjecture, they proved there's a gap, so they prove that this is strictly less than M3. And if you think about it, the Lawson examples, or you think about Frank's talk yesterday with desingularization, if I take two totally geodesic two spheres in the three-sphere that intersect along a geodesic arc, and you desingularize, put in handles along the intersection. So think of two planes as the intersection. So you can put in a Shirk-type surface. You can put in more and more handles, and the areas will converge, if you think about it, monotonically to 8 pi. So you can get 8 pi. I don't know if there is a compact embedded minimal surface in the three-sphere whose area is equal to 8 pi. I don't know. But what this shows is that these numbers are not discrete on the real line. So these numbers go up to 8 pi like this. It's not a discrete set. Perhaps it's true that it's always the case that on the upper side of such a number, it is discrete. If I take a compact embedded minimal surface, perhaps, but who knows, perhaps there is no sequence of minimal surface whose areas converged to that area from above. So these are questions that would be really nice to have information about. In any case, I really started thinking about this in hyperbolic three manifolds. So my real questions are, and consider M3 hyperbolic three manifolds. So their problem is M1 of M3 greater than 2 pi. So as Laurent announced in his talk, we can prove that if the Hagar genus is greater than or equal to 6, then it is true. If the Hagar genus is at least 6, and the answer is yes. But It should be true in general, but maybe it's not. We don't know. Another question is, so in these manifolds, these hyperbolic manifolds, you do have closed embedded minimal surfaces that realize the minimum of the areas among all closed embedded minimal surfaces. What is a hyperbolic 3 manifold such that M1 of that is less than or equal to the M1s of any other closed hyperbolic 3 manifold? I have no idea what the candidate should be. So what is the M3 hyperbolic, closed hyperbolic, such that M1 of M3 is the minimum among all such hyperbolic 3 manifolds? And if you can figure that out, what is the minimal surface in there that realizes the minimum? What is a minimal surface, maybe not unique, what is a minimal surface in there that realizes the minimum? The same kind of question, the same invariance makes sense for cusped hyperbolic 3 manifolds, finite volume. So the same problems, same questions about these invariants in M3 hyperbolic complete finite volume. Hyperbolic finite volume. There, at least I have some idea of what a possible candidate is that minimizes the area, although I have no way to estimate the area of the minimal surface in question. The figure 8 knot and a Seifert surface with the figure 8 knot with the hyperbolic structure. So take a least area torus minus a point whose boundary is the figure 8 knot in the hyperbolic metric. Then the area of that, which is less than 4 pi, I know it's less than 4 pi. I don't know a good lower bound for that area. But that seems, among all the things I've looked at in hyperbolic geometry, the simplest possible minimal surface that can come up this way.
Can I ask a question about your question?
Sure.
Can't you realize a totally geodesic triply punctured sphere in a drilling? Does that count?
A totally geodesic sphere?
Yeah, triply punctured sphere inside a...
Right, you could certainly realize the embedded example.
This would be embedded.
That has area equal to 2 pi or 4 pi. This is 2 pi times the Euler characteristic, which is
2 pi.
Which is 2 pi. Yeah, that area is 2 pi. So maybe that's the minimizer. Maybe that's
Can't
the
get
minimizer.
much smaller than that.
Usually, the totally geodesic one has more area than anything else. See, when you look at stable minimal surfaces in hyperbolic 3 manifolds, the area is less than or equal to 2 pi times the absolute value of the Euler characteristic.
Mm-hmm.
That's the Gauss equation for all sigma, and is greater than or equal to pi times the absolute value of the Euler characteristic.
Okay.
And it's totally geodesic if and only if it's equal to 2 pi times the absolute value.
Mm-hmm.
So maybe there are minimal 3 punctured spheres that are not totally geodesic. If they're incompressible, they're totally geodesic. If it's embedded, even if it's embedded, right, no, that's our theorem, right. Right, it has to be incompressible, yeah.
No, but in the supernote of the figure 8 knot, you have a torus minus a point which has less area as a geodesic sphere.
Right, it's not totally geodesic. It has less area than totally geodesic. Right. Oh, but the totally geodesic for a torus minus a point would have area equal to 2 pi. Yeah, so the 3 punctured sphere is not the minimum. The totally geodesic 3 punctured sphere is not the minimum because the Seifert surface is not totally geodesic and its area is strictly less than 2 pi. Right.
Gotcha.
Right. So, Graham?
Yeah, question.
Yeah. Hi. Just a small question about your question as well. I think these problems, these questions, are very, very beautiful questions. I'd really love to know the answer. But one question in particular I have: these numbers, these little M1 S3, that sequence of numbers there, the minimal area of surfaces of a given genus inside S3. Is there any conjectured asymptotic formula for these MK as k tends to infinity?
Not even in S3 one doesn't know the answer to that. No. It goes to infinity in S3.
Right.
It goes to infinity. It's not even obvious that it goes to infinity in any three manifold. I have no idea. Understand these numbers. How are they related to the geometry of M?
Indeed.
When you think of how hard it is in S3 to understand the numbers, gives you some humility with respect to the problem. I mean, to get from 2 pi to 4 pi to 2 pi squared, M1 to M2 in S3, is a very, very deep theorem as far as I'm concerned. It's all the minimax theory of their paper. It's the Wilmore conjecture. Just to get from 4 pi to 2 pi squared in S3. So understanding this in other three manifolds is going to be difficult, I think, unless somebody comes up with some other ideas. I mean, Fernando and Andre proved that in S3, any embedded genus G surface, G greater than or equal to 1, has area greater than or equal to 2 pi squared. So between G equal genus 0 and genus 1, is 4 pi and 2 pi squared. Okay, so I'll pass the...
Any other
somebody else?
Intrepid volunteers? Okay, great.
Thank you. So I want just to mention the problem, which is probably familiar to many people here, but anyways, it's about volumes now. So the Harold's question was about area. I want to mention a question about minimal volume. So let M an n-dimensional hyperbolic manifold or orbifold which is we can assume that it's compact or non-compact. So there are 4 possible cases here, right? And we know that the volume, hyperbolic volume of Mn is bounded below by a constant which depends on n. This is Kazhdan-Margulis theorem. So we can define these 4 constants. In dimension 3, thanks to the work of many people, some here, we now know precisely all these 4 numbers. In higher dimension, the situation is much worse because, okay, Kazhdan-Margulis theorem can be made effective, so we know that each of these constants is bounded below by a function which behaves like something 1 over super exponentially increasing function of n. So when dimension grows, the bound diminishes very quickly. It becomes practically 0. So think of 1 over n factorial. Well, there is a case of even dimensional manifolds where we have Euler characteristics, so we know better there. But okay, for odd dimensions, you cannot say, and any of these cases, you cannot say more than this in general. And so the conjecture is that each of these numbers should be bounded below by some concrete super function which increases, which is super exponentially increasing. So minimal volume in high dimensions is very, very large. This is what we know precisely this function and examples from arithmetic orbifolds, manifold, no, arithmetic orbifolds, yeah, we know. And these are the natural candidates for minimal volume, but it's very much open conjecture, and you see that, I mean, when you go to higher dimensions, in dimension 3, the gap between, well, in dimension 3 we now know the answer, but also the gap between the estimate from Kazhdan-Margulis theorem and the actual minimal volume is not that huge, but if you go, say, to dimension 10, it becomes extremely large. And the other question which, so this was first question, or conjecture, and the other, conjecture 2, which maybe doesn't look directly related, but it is related, and in fact it's simpler, I think. The conjecture says that now if we look at compact hyperbolic n manifold, Mn compact hyperbolic, the conjecture says that there exists, if n is bigger than 3, there exists a non-compact manifold of the same dimension with smaller volume. Strictly smaller than M. So other way to say it is that in all dimensions different from 3, the volume of cusped manifolds, or Euler characteristic of cusped manifolds is smaller than any closed one. Well, there exists a cusped manifold whose volume is strictly smaller than. Well, in dimension 3, the situation is different. You can take a cusp manifold and do then filling on it, and it will produce a closed manifold with smaller volume. You can only do it in dimension 3, and well, the conjecture is that. Again, we have arithmetic evidence for this conjecture, but in general, it's very much open. So, yeah. Graham? No?
So, anyone else?
Right. This is a minimal surfaces conjecture, which I'm quite fond of. It's based on a result, quite old result, Brian White. Given that I didn't come here prepared, I'm going to get a few details a little bit wrong. So if anybody likes the idea and wants to know the exact statement of the problem, then just come and ask me. Start with a free sphere. S free, furnished with a metric different from the standard Euclidean metric. So you take a metric G, such that G is positive Ricci curvature. Just to say that the Ricci curvature is a positive definite form. Then there's a theorem by White, Brian White, that there exists at least one embedded minimal torus. The conjecture. Now this theorem is proven using using degree theoretic techniques, differential topology in infinite dimensions. The conjecture, which I like to call the White conjecture, I asked Brian White about this, he's cool about that. So, the White conjecture is this: for generic G, with positive Ritchie curvature, there exist at least 9 embedded minimal tori. And by 9, I mean that they are inequivalent by reparametrization, a really different tori. So naturally, if this result is proven using degree theoretic techniques, one would expect this result to be proven by Morse theoretic techniques in infinite dimensions. That is, some sort of Morse-Floer homology for minimal surfaces over the sphere. It's a very difficult problem. Similar problem in the ball. I'm sorry, who said that? I don't assume an ambient isometry. G is generic, so there's no reason to assume an ambient isometry. So they're very much distinct tori. In a similar vein, recent result by myself, Davi Maximo, and Evaldo Paes Nunes, says that if you have a ball, B free, furnished with a metric G, whose Ritchie curvature is positive definite, and whose boundary is convex, then, just like White, there exists at least one free boundary minimal catenoid. Here I'm going to have a bit of trouble remembering the right number. So the equivalent of the White conjecture, in this case, is, I think it's free. So for generic G, satisfying these properties, there exists at least free. I'll put a question mark because that might not be the right number. I can't remember anymore. It's a whole family of these conjectures which you can ask for various other structures, various other topologies. You can ask the same sort of conjecture for different types of manifolds, but the central one that really interests me right now is this one, this one. It strikes me as a very hard problem. The impression I get is that Brian White had this idea, didn't write it. He seems to have been going in this direction in his early research. He never said it explicitly. And then he moved off into mean curvature flows, which is a natural place to go if you're interested in this problem. So although Brian White never explicitly said he was interested in this problem, I would get the feeling that that's what he was trying to do. Anyway, that's the conjecture. Misha.
How you get the conjectural numbers?
As I said, I haven't prepared, so some details are going to be a little bit wrong, but I'll give you the general idea. These problems are homological problems. Okay? These numbers come from homology. The central idea in White's result is to show that from the point of view of differential topological degree, the space of embedded minimal tori is equivalent to product of 2 copies of RP2. Okay? Then you can show that the number of minimal surfaces is equal to the Morse characteristic. Euler characteristic. The Euler characteristic of this thing is 1, ergo 1 minimal surface. If you do homology, you expect the number of minimal surfaces, which you think of as the critical points of a function, to be equal to the sum of the Betti numbers. And some of the Betti numbers are here. It's 3 times 3 is 9. That's the point. So there's this homological idea underlying the origin of these numbers.
Okay, anyone else? All right. Well, thanks for playing.